Okay, I've collected these terms in this expression. So this is our expression for the A vector, put in simplified form where we factored out a constant and have something times the I vector plus something times the J vector. And I think I need to close that parenthesis on the end here. Okay. Now I want to go back to these expressions. Okay, we have this part of the expression. And let's note that this part of the expression, if I take the dot product of this part of the expression that's circled in yellow here with the V vector, I'm going to get 0 because I have a negative cosine times a sine and then a negative sine times a positive cosine. I'm going to get a sine cosine and a negative sine cosine of the same argument in all cases, and that's going to give me 0, meaning that this is the component of A perpendicular to the velocity. So this thing in yellow here, circled in yellow, is just the A perpendicular. And what's the meaning of A perpendicular? Well, let's first look at what's happened to A perpendicular. The part in the parentheses here, the part of this vector in parentheses has constant magnitude of 1, so that the magnitude of this component of the acceleration is constant, pi squared over 4 times A, multiplied by t squared. Well, what's that mean? That means that this component of the acceleration is increasing in magnitude. Now, what happens if you go around the circle faster and faster? You need more and more force, centripetal force, to hold you in the circle. If you want to verify that, go someplace really safe, put on some safety equipment, and drive your car around in a circle, speeding up. And you'll find out where that A perpendicular component is. Now, that's probably better to do in your imagination than to do it physically, because you know, all kinds of bad things can happen. So I'm not recommending that, but think about that. Think about what would happen. Go around a circle faster and faster and faster and faster. Eventually you're going to spin out because friction's not going to provide enough centripetal force to hold you in that circle. Anyhow, in this picture, I've only drawn 2 of the A perpendicular vectors, one for here and one for here. But it should be clear that since velocity is increasing, the centripetal force is going to increase. And that's verified by this calculation. Now the A parallel, what do we see about it? Well, the part in parentheses here again has magnitude 1, and this whole thing is just constant. It has a magnitude of pi over 2A, which means that you have a constant acceleration in the direction of motion around this circle, and the magnitude is just pi over 2 times A. It means you're speeding up at a constant rate. And I haven't drawn that, but you see that the velocity vectors are increasing, and they increase by equal amounts on equal time intervals. Now, we know that we can calculate A parallel by projecting the A vector on the V vector. Saw that previously. And we've pretty much done that. Okay, so that's actually a fairly simple calculation. You should actually do that calculation. You should dot this vector with the V vector and see that when you do and calculate the projection, you dot it, you divide by the magnitude of V, and then you multiply by the V vector divided by its own magnitude, and you get the A parallel vector, and you're going to get this. And then you subtract that vector from the A vector, from the A of t vector, from this whole vector here, and you're going to get this. And it's kind of a neat little circle. It's worth doing. It's worth actually doing those calculations. They aren't that hard. You just have to keep track. You're going to need a whole page of paper, but you're not going to need reams of paper. And you just write it out carefully, make sure everything comes out. Good way to check your algebra, good way to check my calculus, in case I made a mistake. And you can get a nice full circle in your reasoning and in your calculations and in your understanding of these vector functions.